started? Okay, let's go. So, welcome everybody. Thank you for coming for the second lecture of the mini course on the architect structures and Opers. Thank you.
Thank you. So, thanks for coming. I'll start with recording what we did and adding a few details just in the some of the questions that appeared and to clarify some of the points. Right? So what we did last time, which was yesterday, we started with a compact surface. Some of the discussion will be local, but for the moment let's start with the compact surface. So we introduced this notion after some preliminary setup. We introduced this notion of a projective or affine with two structures. So a projective affine structure on X was an equivalence class of atlases with special property. So an equivalence class of projective for affine atlases. So this meant that, okay, so our atlas, let's say, is a collection of local charts. These z alphas will be the coordinates. And we put a restriction on the transition functions of this atlas. So if we look at these z alpha beta, right, which is z alpha after z beta inverse, right? So where do these go? As you know, these go from z beta, if you alpha beta, z alpha, if you alpha beta. So these are a bunch of functions from an open set in C to an open set in C. We require that these satisfy some, or there are two ways of saying it. At the end of the day, we require that these are either fractional linear transformations, so Mervillus transformation, if we're talking about the projective structure, or just affine, if we're talking about this affine structure. So we're looking for an atlas. I mean, we have, at the end of the day, we essentially got to a place where we can discuss existence. I mean, just become clear with the final theorem. We're looking for an atlas where you can pass from one chart to another by fractional linear transformation, or in the other case, is by affine transformation, right? Affine English, right? So this was placed in terms of the requirement that these phi alpha beta satisfy some differential equation, right? So that was essentially the way we started. This means so these phi alpha beta satisfy. So if I'm talking about an affine structure, they satisfy the equation f double over f prime. So we call this operator theta 1 of f being 0. So this is called affine structure. And for the projective case, we require that these are annihilated by the Schwarzian derivative, right? So we wrote it as f of f. There are a couple of ways of writing this operator, actually more than a couple. You can think of this as f double over f prime prime minus half f double over f prime squared. So this looks like theta 1 prime minus half theta 2 squared Well, of course, you could write this as twice f prime f2 minus who? Minus 2 times f double squared. Right? So this should be 0. Right? So in the first case, right, the transition, so this is for the projective setup. In the first case, in the affine case, the transition functions are annihilated by this differential operator, which means they should be affine linear. In the second case, they should be either this should be 0 or the Schwarz-Sierra of each transition function should be 0. Right? So really, it's direct to see that if you have a fractional linear transformation, its Schwarz-Sierra derivative is 0, and we gave one argument why the converse hold, that if we have a function whose Schwarz-Sierra derivative is 0, this is actually going to be fractional linear. Actually, I'll show you a second way to see this. Alright, so it's a kind of equivalence path of atlases, and the equivalence is the union of two atlases is again such an atlas. That's the equivalence relation. So we're going to be working with a Riemann surface. So we have the complex structure fixed, right? In principle, you would start with a topological surface and ask if this condition holds. So if this condition holds, you would get yourself a complex structure. So in principle, one could be looking at complex structures that are not necessarily, so it could be looking at affine or projective structures that are not necessarily compatible with the structure you start with. So we're not going to do that. So we're always going to be assuming that the complex structure determined by this atlas is the same as the original one that we're starting with. Right? So we're looking at complex projective structures, if you wish. Right? The real projective structures, there are many more of them. Okay. So as part of the introductory discussion, we saw actually one of the thing that comes in a number of times is a kind of chain rule or a cocycle property of the Schwarz-Sierra derivative. Actually, also of this will go to the derivative of f, right? So this is actually one of the key local features that make this work. So we have a kind of chain rule for both of these, for delta 1 and delta 2. Let's say delta r is 1 and 2. And if we set h to be the composition of two functions, so let's say w is f of z, then what you get for the delta r for h W is that this breaks into a sum of two pieces. One is theta r of g W times the derivative of f prime to r. So it's either just the derivative or the derivative squared, f prime of z, if you wish. Plus another piece, which is just this theta r of f. Let's see. Again, here r is 1 or 2. So for the affine case, if this is the differential operator, the differential operator is the logarithmic derivative of f prime, which This is just proportional to the, its exponent is crucial here. It's proportional to f prime, otherwise we have r squared. So this looks a little bit annoying, well, at least a little bit unclear somehow. How can we think of this? You can, first of all, it's more interesting to look at this at theta 2, right? Because affine transformations are a special case of fractional linear. So we can write this actually a little bit nicer. You can write it in terms of quadratic differentials. Actually, I should have maybe kept this. So let's look at the case r equals 2 first. So we can write this the last identity as let's say so s of h, or let's put it like this. I'm having something funny. Yeah, okay, so I'm looking at z is the variable in the domain, so this is g of f of z. Apologies for this. So we can think of this as s of h, so sh of z, z squared is being, I'm using writing the variable as a subscript. S w g w squared plus s of z f squared. So you can think in terms of quadratic differentials, this becomes a little bit more symmetric, right? As the Schwarzian is just theta 2, and I'm keeping track of the value. So I'm saying that this section here, which is theta 2 of h, and theta 2 of the composition, right? This is squared. The fudge factor here is the derivative squared. That's why the dw squared appears here. So if you stare at this, you see a number of special cases that we're kind of illuminating. So we can take either f or g to be a fractional linear to see what happens. So so we can either decompose or post-compose the fractional linear transformation. So if we take, let's say, f to be fractional linear, so this w, which is f of z, is z plus b over cz plus d, then this term will be gone, right? Because fractional transformations are annihilated by the Schwarzian. So we get that sz of g after f dz squared is sw, so only this term survives. Swg w squared. So this is saying that if we allow only fractional linear changes of coordinates, the Schwarzian derivative transforms like a quadratic differential. This quantity is the quadratic differential. Now, if we take the other function to be fractional linear, so I'm looking at two special cases. So if we take, let's say, G of W to be AW equals B equals CW equals D. So if we take G to the fractional linear, then this term would be gone. And we're just getting invariance, right? It's Z of G after n is the squared is this Z of Z squared. Right? So we have a kind of invariance property. So essentially, these are two of the kind of miraculous properties of the Schwarzian. Actually, if same thing works, so if R is 1, we would have the same, well, we would have here dz dw. So we can rewrite this chain rule in terms of usual differentials, not in terms of quadratic differentials. So this is saying, well, the first identity is saying that if we adjust the one coordinate transformation that the fractional linear, the Schwarzian behaves like a quadratic differential. The second is saying that if we oppose composing a function with a fractional linear transformation, its Schwarzian is staying invariant. So in a way, one could try to push. We had a discussion at the end of last talk, right? One could try to push this in other directions, and let's say maybe to play with different differential operators, right? So first of all, for dimension 1, Cartan proved that these two theta 1 and theta 2 are the only pseudo groups that arise from differential operators. Again, maybe you could try to push this, in other dimensions. Probably Cartan has done some of this, but you would need some kind of property like this for the theory to behave similarly. So this is not any old operator; it's an operator with a special property. So that's one thing. So I just want to. Is this making sense? Just please stop again if there are any questions, either philosophical or technical nature so far. I haven't done much. I just rewrote this chain rule in terms of global terms. Right? Differentials are better than derivatives. So if you think the Schwarzian is linked to quadratic differentials, so this is these two special cases are important. So what
happens if they're both? If they're both fractional linear transformations?
Well, then this would be dead, right? Because if on the first stage you get this, and then if f is fractional linear, it will be also 0. So one could try to solve, some of the local questions that appear in this theory boil down to solving a differential equation where you have Schwarzian equaling some other function. So there's an interesting proposition which probably comes from Schwarz already, or since he knew, right? That links solutions to the third order equation that involves Schwarzian to solutions to a second order linear equation. So I want to add this. Yesterday I was thinking of mentioning it, but we didn't get to that. So I'm reviewing, but I'm inserting a new bit. So it's a local statement to the statement on an open set on a domain in C, essentially. So that's another question that appeared in the discussion. So we have the following proposition. I go to Schwarz. I'm never sure whether there's a T or no T there. If we have a solution to so if f is the solution to everything is local. I'm not writing the domains. Everything will be on the domain in C. So if we're looking at solutions to this equation, S sub z of f being some function q of z, some q, then you can write it actually as a ratio of two solutions. So you can write it as y1 over y2, where the y's, these yi, are two linearly independent solutions to the equation y double plus qy equals 0. Right? So there's a q over 2. This is the same function. And actually, conversely, if you get any solution to this equation, the ratio, a pair of solutions to this equation, the ratio would satisfy the one on top. Let me label these as star and double star. So conversely, yi are two linearly independent solutions of double star, then the ratio f, which is y1 over y2, satisfies the equation on top. I'll go into maybe some of the proof. The proof is, again, it's kind of calculus, but it's you can see some of the sort of very specific behavior of this structure that enters. So this is a kind of perplexing result if you see it first, right? Because on top we have some solution of a third order nonlinear differential equation, right? While here you have a linear second order equation. Essentially, we're saying the solutions of the one on top are the projectivization of the space of solutions of the one here. Right? So.
This is the link to the classical stuff where you get the equation of Dr. and Kadevin,
Indeed, yeah.
modified, and then the sinus Gordon.
Right. So this is a kind of, you can think of the kind of Schrodinger equation.
Potential Q.
Yeah, potential Q, right. The proof is kind of fundamental, but let me just outline it because there are two ingredients that you need, well, in both directions. So let's say we're going in the direction that star implies double star. So we have a function that satisfies this equation. Right? So we consider f such that the Schweitzer derivative of this function q. Right? So we're trying to write it as a ratio of two functions that satisfy another equation. So the first idea is look at so set y. We figure which way I'm going this way. So set y to be 1 over the root of f prime. Again, we are making, so here f prime is it's never going to be 0 in our situations, right? First of all, f prime, for example, would be our transition functions are homomorphisms. So we're picking a branch. So, and then we're going to check that, I'll call this maybe, okay, I'll call this y, and then we're going to check that this y, and f times y satisfy our style. So, I mean, essentially, I think for most of you, this is enough. But let's, I was promising to be trying to be somewhat pedagogical. So we what do we know? We know that well, we know that the Schwarzian derivative of this is q. So I'm going to set just to in the Schwarzian that is repeated f double over f prime. So to make just the calculation simpler, I'm going to temporarily set f to be phi to be f prime over there. Right? So then the Schwarzian S sub z of f, right, is phi prime over phi prime minus a half phi prime over phi squared. And this is supposed to be q, right? This is supposed to be q, and our y, just getting back to this notation, right? So y is 1 over the root of phi in this notation. So then you just check that the double star is satisfied, right? So what do we have? So y prime, right, is minus a half phi prime phi to the half. So you can think of this as y, so this is minus a half y times phi prime over phi. Right? So then double y double prime, which you can shape once more, right? Y double prime is minus a half y prime phi prime phi minus a half y phi prime phi prime, right? And then we plug the previous step in, right? So this is a quarter y phi prime over phi squared. Minus a half prime. So this is the Schwarzian up to multiplied by y, actually 1/2. So this is 1/2.
It's minus 1/2.
Minus 1/2, right? Schwarzian times y, and this is am I my, yeah, this is Q. Yeah, this is not a half Q, this is a Q. And so it's a half Q times 1. And we get the backward myopia. Right, so that's the other check is exactly the same. So we check that this solution, so there was a bit of, so one idea here was to consider one of the root of it, and then we check that it satisfies this linear equation and similar for the other solution. Right? So that is in this direction. Now, in the opposite direction, so similarly for f times 1, it's also set. And we need to check that this would be y1 and y2, so this would satisfy the two. Those are the two solutions. Now, in the opposite direction, so we're starting with one solution of the second order equation, right? Yeah, this is kind of a standard trick. So let's say y1, y2 are linearly independent solutions to double star. Right. So then when you look at the Gaussian would end up being a constant. Right? So look at y1, y2 prime, y1, y2. Right? So W prime, right, is y2 prime, y1 prime, plus y2, y1 double, minus y1 prime, y2 prime, minus y1, y2 double. Right, so these two cancel, and we're getting, right, since both of these satisfy the equation, this is minus half q times y1. And the other term here is minus y1, y2 double. It's minus half q y2. Right, so this is 0. So the Gaussian is constant. You can always normalize it to make it 1. So equals to 1, right? So we have y2, y1 prime minus y1, y2 prime is 1. So this would give some huge simplification on what the Schweitzer derivative looks like. That would be the idea now. So consider the ratio. So we have this, right? We're starting with two solutions of the second order equation. We have this identity, so we consider y1 over y2 is Schweitzer derivative y1 over y2. Right? So I'll call this would be f. Right, so then when you work this out, right, you can trade, so you have y1 prime, y2, minus y1, y2 prime, or y2 squared, but now you can trade derivatives, right? So this is just going to be y1, for example, prime y2, would be y1, y2 prime plus 1. So this would be just 1 over y2 squared. Right? So so then the zero will work the second derivative. So F double, right? Now that we know this y2 squared prime, right? This is minus 2 y2 prime over y2 cubed. So what happens with the Schwarzen? So we need f prime over f, so f double over f prime. So this is just going to be minus 2 y2 prime over y2. Right? The y2 cubed is cancelling with y2 squared. And so S sub z of f is minus 2 y2 prime over y2 prime minus a half, and that would be 4 times y2 prime over y2 squared. So when you just checking my one halves in place. Right. So when you simplify this, right, you're getting minus 2 y2 double over which is our cube. Okay, since the function satisfies the differential equation. And so we so there is again this kind of technical element, the technical, but shows that there is some interesting feature of this third order equation that has some actually something linear associated to it. That there's a linear equation that is so this linearity. All right. So let's see. I don't have the original statement now, but so there are a couple of interesting corollaries.
Who did this computation for the first time?
I mean, so Turing references Schwarz.
Schwarz.
Yes. Or so. He says Turing says that it goes back to Schwarz. So in some form it should be Schwarz. I haven't traced it all the way there, but yeah.
This is not the Russian Schwarz. This is another.
But this is the Schwarz to the Schwarz to it's not Russian Schwarz, right? So this is what means.
Well, maybe who invented the list of solutions of hypergeometry, algebraic solutions.
Right.
Found that actually in the same way.
Hermann Schwarz. Hermann Schwarz.
Hermann Schwarz.
Hermann Schwarz.
So is it with the T or without the T? Because
It's without the T and without the S.
No, all right.
Hermann Schwarz.
Hermann.
Hermann Schwarz.
So couple of things that fall out immediately. Immediately from this. So there's a couple of corollaries here. So first of all, we get another proof that the functions that are annihilated by the Schwarzian are precisely fractional linear. So it's just subjected that the 0 implies that f z is equals b over c equals b, right? Because right, this is clear because our f is a ratio of two of these, but now the equation is so the equation is just the derivatives like are 0. The second derivatives are 0, right? So the q is 0 in this case, right? So we have a slightly different proof last time, where we rule out the Schwarzian derivative in some way using games. So that's one. So again, there is this actually whole parallel between the affine and the projective case, right? The affine functions are the ones that are annihilated by the second derivatives. Here, the fractional linears are the ones that are annihilated by the Schwarz. Another proposition is that if you take, let's consider two functions whose Schwarzian derivative is the same, right? So if s z of f1 equals s of z of f2, then one is obtained by the other by a fractional linear transformation. Say f2 is a times this is again, so this is the analog of the statement that if two functions have the same derivative but they differ by a constant that on a connected set. Here they one is obtained from the other by a fractional linear. So indeed, if we whatever this function is, this value is the q, right? We have that we'll be able to write each of the functions as a ratio of some two solutions to the same equation, right? So f1 would be y1 over y2, and let's say f2 would be the ratio of some other solutions at y1 to over y2. Right? Both of these are linearly independent. So yi independent solutions of q. So y is q to y is 0, and the yi tildes are also like that. Right? So each of the yi tildes is a combination, linear combination of the respective others. So tilde interior combination y1 right? So they satisfy the same differential equation. one terminal independent, so we have to use the combination. Yeah. So earlier we had from the chain rule kind of property of the Schwarzian, we had that if we compose f with a fractional linear, the Schwarzian doesn't change. Here we are going kind of in the opposite direction. We take two functions with the same Schwarzian, they are obtained by, they differ by a fractional linear. So if you play with the formula, actually you can see already at this point that if the Q transforms like a quadratic differential, like section of k squared under changing coordinates, these yi's transform like sections of k1 half. So like half relative half. All right. So we're having this kind of local properties of the power transition function that we want to get. All right. So we also mentioned. So last time we ended up essentially with finding an abstraction to the existence of this type. And for the moment, these were local calculations, and we want to have an atlas with such transition functions. So we discussed also the abstraction. Essentially, the abstraction to the existence of these projective or respectively affine affine structures on our X. Again, for the moment, X will be compact surface, although actually the argument works for an open surface as well. So the abstraction is a particular cocycle, and so in C1 of k squared. Right? So let's say we fix an atlas again, fix any atlas. And we looked at a particular class in let's say C1. We check C1 with respect to this cover of k squared. Sorry, k to the r, right? This is r inside the 1 and 2. Which is, this class was essentially obtained by applying the differential operators theta 1 and theta 2 to the transition functions, right? So you pick an atlas, whatever the transition functions be alpha beta, or you apply the Schwarzian derivative to them, and you get a function on each intersections of opens, and we satisfy the cocycle condition because of the property, the general property for the Schwarzian, or for theta 1 as well. So this is a class in so this class actually is a compound. And so this is actually in sorry, this class, well, it will turn out to be a compound, but for the moment we don't know. This class for the moment is just a cycle. That's where we ended up. So it may or may not be a compound a priori. We don't know yet. Again, Jan uses this terminology of projective for affine connections for an element in C0 whose say organic, right, is known in C0, the coefficients in either k or k squared, such that delta H is this respective class. Again, this may or may not exist. So this class, again, this class is not zero. Cohomologically, there wouldn't be such a knowledge. If it is zero, cohomologically, there will be some H. That there could be much more of them, and actually, when you stare at this, if you haven't thought about it, if you have once you have one such class, right, the set of all of these, all of them would be, well, the difference would be a global section of k or k squared. Okay. Yes. So now, so if the difference of two such connections is, let's say H1 and H2, right, is in H0 a x k to the power x, right? So in other words, in H0 k squared or projective connections in H0 k for the alpha. And so we know actually what I'm saying is the case of these, so these zero cross cycles, right? If we have at least one, then the space of all such is actually, well, is a set of quadratic differentials, right? I mean, just the difference of two, right? Delta H1 minus H2 would be zero, so this is a global section of the respective point. So the space of all such projective connections is just the space of quadratic differentials, and it's just the space of the brilliant differentials if we're looking for the alpha exponential. Right? So the theorem that I want to say a couple of words about the proof of the theorem that we formulated last time. This is just the key part of the proof. So the theorem was that there is a one-to-one, there is canonical one-to-one correspondence between projective or affine connections in this sense on X and projective or affine structures. And actually, this is true. This is true even without the assumption of compactness. And so it's true also on this assumption. So for an open with uncertainty, it would be also true. Right. So we're saying that there are as many. Let's talk about just projective, right? One is special case of the other. So projective structures on the curve, as there are classes in C0 of k squared, respect to a cover. Okay, when we define the structure, we pass to the equivalence class of the lattices. So this is part of the discussion. But you need to, there are as many choices of this H, again up to equivalence, as there are equivalence classes of projective atlases with various transition functions. So I mean, non-canonically, we know that if there is at least one, then there will be as many as h0 of k squared. We don't know yet. We don't have a canonical choice of one. Okay, maybe if you appeal to uniformization, you would have a canonical choice. But we have a choice of one. And we don't know if we have at least one, but we know that they are in projection. These h's with the upper projection. So here is maybe just the outline. So let's say you start with some atlas, U alpha. So let's say U alpha Z alpha is some atlas, not necessarily practical projective. So now if we could be going both ways. Right? We would be trying to find a projective atlas starting from the connection. So if we have another atlas after refinement, we can assume that the views are the same and just the functions Z alpha are changing. So any equivalent atlas we assume to be taken to be let's say having the same opens and just some other coordinate functions, right? These are the original ones composed with something, so some G alpha after Z, right? And G alphas are local analytical homomorphisms. So after refining the cover, passing to a common refinement, an equivalent atlas would differ from this one by composing with some G alphas. This is the composition. So with this new atlas, we'll have new transition functions. So let's say the transition functions here are phi alpha beta. So with this equivalent atlas, we'll have some phi alpha beta star, right, which will be obtained from these by conjugating with G alpha and G beta, right? So this is G alpha after G alpha beta after G beta inverse, right? So if what's the condition for these functions to be fractional linear? So if we are starting, if we're starting with the projective for affine connection, we'll be trying to choose the G alphas so that these are fractional linear. So this new atlas will be fractional linear if this new atlas will be projective or affine. Well, if theta r of these functions is now dead, right? But the theta r of these functions, applying the chain rule syntax, right, is minus theta r g beta plus theta r phi alpha beta plus theta r g alpha times the fudge factor that came from the derivative to the r prime. And we applied the chain rule type property for this operator 3 times. So if I'm looking for an equivalent atlas where the functions are affine or projective, well, that's some condition on the G alphas. So let me just move one to one side. So theta r phi alpha beta. Well, this is a kind of differential equation on the phi alpha beta that involves well, the difference of theta r g alpha phi alpha beta prime minus theta r g. So right, so what is this starting to look like? Right? This is our Gauss cycle, and this is our Gauss cycle CR, alpha beta. And essentially, if we find the G's, we will be representing it as a covalent. Right? So let's say, so we're going to set H alpha to be right, so we're getting essentially two equations as a relation here between the H's, the G's, and the P's. Right, so we're having this Gauss cycle CR, so theta r phi alpha beta is H beta minus H alpha times R, and the H alpha is here. Just I want to have it as in one place. I'll put there's a negative sign to make the check homology correctly. So if you now depends. The statement is about an existence of canonical one-to-one correspondence. Right? So if we start with any atlas and want to find the G's, that would make this expression 0. We have to solve a differential equation for the function g alpha. So the question here of finding the g alpha, so locally the question boils down to solving this differential equation, right? So let's say if you give me the projective connection, how do I find the projective structure? You're giving me the h alpha, we have to solve locally this differential equation, the Schwarzian of g equaling h, or the second logarithmic, whatever, f double over f line g equaling h alpha. So if we so for example, given h alpha, find the alpha delta star, we need to solve the differential equation with our g alpha is minus h alpha. So this is the kind of differential equation that we had in the beginning. And so locally the problem boils down to existence of a solution to this type of equation. If you're giving me the h's, we have to use the existence result for g alpha. For example, passing through the second order differential equation. So we find the g alphas. So we go to the co-cycle that is now with constant transition functions. And if we're going the other way, we can pick the g alphas and get the co-cycle h alpha. Now one has to check that this works with the equivalences, right? We have projective structures in equivalence class of atlases, so this whole procedure is compatible with passing to equivalence classes. And essentially, it is compatible because of the properties of the Schwarzian that we went through. Is this making sense? Okay. Right. So I would. So just a couple of immediate corollaries. So first of all, any open within a surface admits an affine structure. So any open within a surface, let's say U, admits affine structure. These are, so the affine structures are equivalent in projection with, well, non-canonical because we need a base point. Projection with Billiard differentials which we form on the surface. So we have a kind of local statement, right? Why is this true? Because h1 of k is 0 on normal, right? On an affine, the higher homology dimensions. So your abstraction class will be dead. So there will be locally, right? So on not on the surface, right? So this will be always some affine structure. Now, on the other hand, any compact, I mean, if I wanted globally, so if I wanted on a compact with a surface, only the genus 1 case pass through this. So any compact real surface includes a projective structure. So these are not canonically in rejection with quadratic differentials. So we have 3G minus 3 dimensional space of projective structures. Again, why? Because the abstraction, we already erased it, but it's delta pi p alpha, that is h1 of k squared is 0, right? So this is h0 of k inverse q. Well, for genus greater than 1, this is the argument. For genus greater than 1 by such duality, this is 0, so the abstraction is vanishing. So you would have at least 1, and then by the argument that the difference of two h's is a section of k squared, you would know that these are in a rejection of k squared. For genus 0 and 1, right, we see it directly. Right? I mean, for genus 1, the structure is actually affine, right? The usual, already the usual average usual sort of policies has affine changes of coordinates. For genus 0, okay. The stereographic atlas gives you a projective structure. So, right, so we have the existence, at least the existence, and we have an idea of how many of these structures are there. Right? Way more time than that I need. So, so the next, so just briefly to wrap it up, to tell you where this would be going. Turns out that there is actually an entirely different description of these objects. So, and it goes as follows. Actually, okay, let's see. So it turns out there is a more geometric. Well, it depends how you consider this geometric or not. There's a more geometric description of projective structures. In a way, it's already clear that if I pass the projective atlas and think of this Laplace transformation that we have for each pair of opens, if I think of them as elements of PGL2, what I'm having is, well, a PGL2 matrix for each coordinate overlap, a constant matrix, and the transition functions are constant, and a fractional linear transformation, so they're given by constant matrix. So what we have is, if we find this projective atlas, it's clear that what we have is a cover, and on each double intersection, we have a constant PGL2 matrix, and these matrices satisfy a cos-cycle condition. So we have an element of H1 of PGL2. So each projective atlas determines, say, determines a class in H1x PGL2 PGO2, but I'm thinking of this as, as the constant sheaf. Like it's a homology of the sheaf with coefficients in a group. But this is not the sheaf PGO2. These are the sections. I'm not looking at the sheaf whose sections are maps from the base to PGO2. This is the sheaf whose sections are locally constant map from the sheaf to the base. Right? So P alpha delta belong to PGO2C, and they satisfy the cross-cycle condition. So this class should correspond to, on one hand, this class should correspond to some flat P1 bundle. You take a flat bundle with fiber P1. So this this class corresponds to a flat P1 meaning CP1. At the same time, one can show so you can think of these elements of H1X PGO2. This class can actually be lifted to SL2. So if you're annoyed by the PGO, you can choosing a cathodic characteristic, you can lift that class. Actually, it comes to SL2. But this, at least as a set, this can be identified with homomorphisms. So representations of the fundamental group into PGO or SL after conjugation. Right? So you can think of this space as space of flat connections, or again representation of the fundamental group of phi 1. So this is a kind of interesting topological object. Actually, it has the structure of the affine algebraic polarity. Stein is not, it's affine actually, so it's affine. So it's clear that, so if we have this atlas, we are getting some kind of Q1 bundle, and some kind of object here that we can think of as a flat connection on the bundle. And just to, I have 5 more minutes, it's like, so just to describe what this ends up being. So this map, by the way, this map that sends a projective structure into this space. This space is big. This map ends up being 1-to-1. So the map that takes. So we have a map from the quadratic differentials. If you want, we have a map from the quadratic differentials to this cohomology group, which is actually again an affine polarity. This is why is this an affine polarity? Pick generators for the fundamental group, and then take a bunch of matrices that satisfy these relations. So this set is a connection of elements in PGO2 cross PGO2 cross PGO2 plus 2G matrices that satisfy the equations and the conditions, the relation of pi 1 mod conjugation. So we're mapping the quadratic differentials to this space. The map is in fact 1-to-1, which is not obvious. The map is in fact 1-to-1. It's very much not onto. The space of projective structures has half the dimension. So this space is actually projective structures has half the dimension of H1. If we work with projective structures that are real, so that are not compatible with the complex structure, the map is not one-to-one. But if we use complex projective structures, the ones that we've been talking about, then it is in fact one-to-one. What this data that we had so far have, it can be described as follows. It's tricky to describe, it's tricky to describe the image, to put it short. So we can describe that. This will take actually mostly next lecture. Describe projective structures in these terms as follows. So here is a sort of picture that it might seem has nothing to do with it. So let's say we have P over X, the principal, let's say PGO to bundle. You can think of SL, we can lift to SL using a data characteristic. This means algebraic. Of course, so we are a compact curve, so we have Gaga, so we can think of this being analytic also. We fix a parallel subgroup in detail. So the upper triangular or the lower triangular. And we look at the reduction. So let's say PV is a reduction. Reduction of the PGL bundle to B bundle. This reduction is essentially, there are different ways of describing reduction of a structure here, but one way to do this is to look at the quotient P mod B to X. Let's say this is, let's say F, and the reduction corresponds to a section here, to a section of this map, right? And we look at the flat connection on P. So I'm describing bits of data that it corresponds to what we had so far. So let's say D is homomorphic connection. So the bundle, everything is now homomorphic or algebraic. The bundle is homomorphic. Principal bundle, we have reduction. We have D, which is homomorphic connection on the bundle. It's automatically flat because in dimension one, so the homomorphic or algebraic connection is flat. There are no 2, 0 points. And so the presence of connection splits the tangent bundle here as a horizontal and a vertical piece. Right? So it splits TF P mod B into two pieces. The vertical it is already there, plus some horizontal bit. So so we can look at the differential of this section. So look at the map that takes Tx to, so this is d sigma. So look at the differential of this map, T and P mod B. And so this breaks into the two pieces. The vertical piece and the horizontal one, and then project onto the, so there's the pull back here, project onto the vertical piece. So I'll call this map sigma bar. This is what you would call we'll need to spell this out. I'm just letting it up for next time. But this is essentially what is called sometimes the second quadratic form of the connection. So it turns out that the projective structure is is equivalent to data P sub D D. So PGL bundle, a reduction to a well, and a connection for which, was forget sigma tilde, such that sigma tilde is an isomorphism. So the statement is that the data we had corresponds to a triple of a principal bundle, principal VGL or SL bundle on the curve, a reduction to a well, and a connection that is flat for dimensional reasons and satisfies a kind of transversality condition. This is, in a way, it's an analog of Griffith's transversality condition in Hodge theory. It would turn out actually that the bundle is fixed. The bundle, I mean, the choice of if you're looking at all such possible data, the bundle P is essentially uniquely fixed, and the only freedom we have is in changing the connection. So the bundle P is a very special bundle that is linked to certain jet bundles. So I'll try to elucidate next time the piece of this picture. So one could take this as a definition, and the question would be that, how do we get these special atlases? So I think I'll 2 minutes, 5 minutes over time. So I'll stop here.
Are there any questions for Peter?
There's some concrete meaning to such representations which land in PGLR or real body.
How are these representations special? Yeah. Maybe there's some work on David Dumas, I guess. I mean, they're kind of. I don't have a good answer to this. There's some work on David Dumas. I mean, these representations are. This space is not only a complex of variety, it's actually a symplectic variety, and the representation that we get form a complex Lagrangian subvariety. But they are very special. They're kind of the speciality comes from is hidden in these special choice atlases. But topologically, it's a bit tricky to say. Topologically, there is the specialties here corresponds to a very special choice of the bundle and the reduction. So essentially, the only freedom that we have in choosing the projective structures is in choosing the connection. So there is a very special bundle. So these elements here can be thought of as a data bundle plus connection, and the bundle is rigidly fixed. Essentially, the bundle is the frame bundle of the first jet bundle of the characteristic, for example. Think of this. And again, I cannot say much about the topology. I think David Dumas had some constructions with dent twists and so on. One to describe these representations. So, thank you.
Are there any more questions? Well, if not, we can thank Peter again. And for those interested, we can go